Hello everyone, my name is Xiangyang Gou from Peking University. This is a presentation video of our paper, Sliding Window-Based Approximate Triangle Counting over Streaming Graphs with Duplicate Edges, published on SIGMOD 2021. Streaming graph is a newly emerging form of graph data. It is organized as an infinite sequence of data items. Each item indicates an edge and its time step. Streaming graphs usually have edge duplications. It means the same edge may appear multiple times with different time steps. In most applications, we only value the most recent data items. We define the data items arriving in the last n time units as a sliding window. The edges in the sliding window are active, and edges out of the sliding window expires. N is the length of the sliding window. It is decided according to the need of the application. Edges in the sliding window form a dynamic graph, and we call it a snapshot graph. The figure on the right shows an example. Different graph analysis algorithms can be implemented on the snapshot graph. Among them, triangle counting is one of the most fundamental tasks. When the streaming graph has edge duplication, there are two semantics for triangle counting. Binary counting only considers the number of distinct triangles. On the other hand, weighted counting gives each triangle a weight, which is multiplication of the three edges frequency. We report the sum of all triangle weights as a result. As the throughput of the streaming graph is high and volatile, the snapshot graph has a large and unpredictable size, and it changes rapidly. Accurate analysis on it is difficult. Therefore, the goal of our research is to design an approximate algorithm to continuously monitor triangle count in the snapshot graph. It should have a bounded memory usage so that we can preserve memory for it. It should also cover both binary and weighted counting semantics. The following table shows the position of our work. As far as we know, our work is the first algorithm to solve the above problem. We propose an algorithm named as sliding window triangle counting, SWTC for short, to solve the above problem. There are two major steps in SWTC. First, we need to maintain a sample of the active edges with bounded memory. These sample edges form a sample graph. We monitor the triangle count in the sample graph. Second, we need to estimate the edge number in the sliding window. At last, we scale up the triangle count in the sample graph to the snapshot graph. There are different requirements of these steps in binary counting and weighted counting. In binary counting, duplicate edges should not be included in sampling or number counting, while in weighted counting, they are equal to distinct edges. We focus on binary counting first. Then we will show how to extend our algorithm to weighted counting with little change. This figure shows the framework of sampling in SWTC. First, we use the hash function h to split the streaming graph into k substreams. We use another hash function j to compute a priority for each edge. We try to select the active edge with the largest priority in each substream as a sample. And the partition of the substreams and computation of priority are all performed with hash functions. Each distinct edge has the same probability to be sampled as a sample edge. The major challenge in this framework is how to select the active edge with the largest priority in each substream with bounded memory. In fact, this problem is very difficult. We first show a naive solution. In each substream, we store a variable epsilon. It is initiated as null. When a new edge E arrives in this substream, we compare E with epsilon. If E has a larger priority, or epsilon is empty, we set epsilon to E. Besides, when the edge stored in epsilon expires, we set epsilon to null. Sadly, this simple strategy does not work because it cannot guarantee that epsilon has the largest priority. The figure on the right shows an example. Each bar represents an edge, and the height of the bar represents its priority. When the edges represented by red bars come, and they have smaller priority than the green one, they are not stored. However, when the green one expires, they are still active and form a blank area. They may have higher priority than the new edges, thus we cannot simply select the new edge, represented by blue bar, as sample edge. Otherwise, the new edge will have a higher sample probability, and the sample will be biased. In fact, it has been proved impossible to get a fixed size sample with bounded memory in sliding window. We have to compromise to a bounded size sample. In SWTC, we used a fixed length slicing strategy. We split the streaming graph into fixed length slices. Each slice has the length of n time units. The sliding window overlaps with at most 2 slices, the ongoing counting slice and the last slice. In each substream, we store 2 edges, epsilon and beta, denoting the edge with the largest priority in current slice and last slice. As each slice is insertion only, it is easy to maintain epsilon and beta. We just need to initiate them as now at the beginning of the slice, and keep comparing them with new edges until the end. If the new edge has a larger priority, we set the variable to the new edge. Then, by comparing epsilon and beta and their time steps, we can try to select the edge with the largest priority in the sliding window. In each substream, the state of epsilon and beta can be divided into 3 cases. In the first case, epsilon and beta are all active. We select the one with larger priority as the sample. In case 2, beta expires, but the sliding window still overlaps with the last slice. We compare the priority of epsilon and beta. If beta has larger priority, we cannot find the active edge with the largest priority, and we give up sampling in this substream. Otherwise, we sample epsilon. As time goes by, the sliding window no longer overlaps with the last slice. Case 2 changes to case 3. In this case, we use epsilon as the sample. After case 3, a new slice comes, and we set beta to current epsilon and set epsilon to null. Case 3 changes back to case 1, and the 3 cases repeat recursively. Now we explain why in case 2 we may not be able to select a sample. If the priority of beta is larger than epsilon, there may be an edge, E, in the last slice. It has priority between epsilon and beta, and is active, as shown in the figure. It is the active edge with the largest priority, but we did not store it. Therefore, we cannot get a valid sample in this substream. As each substream has an equal probability to abandon sampling, the sample graph we get is no larger than k edges, but the produced sample is uniform. The size of the sample graph varies with the throughput of the streaming graph, and it also waves in a circle as the length of the current slice changes. When the throughput of the streaming graph is steady, the average size of the sample graph is 0.75 k edges. We need to continuously monitor the triangle count in the sample graph. Whenever a sample edge is added to or deleted from the sample graph, we can count the number of triangles it induces, and add the number to the triangle count, or minus the number from the count. Detailed algorithm of maintaining the sample graph and the triangle count can be found in our paper. The second major step of SWTC is to estimate the number of distinct edges in the sliding window, namely the cardinality. We can solve this problem based on the fixed length slicing strategy. In each substream, we can transform the priority of the 2 stored edges into a variable R, which obeys a geometric one-twice distribution. Then we can perform hyperlog algorithm on the k variables in the k substreams and get an approximation of the cardinality of the most recent two slices. Hyperlog-log algorithm is a widely used approximate algorithm for cardinality estimation in insertion-only size. Detailed steps of the transformation and hyperlog-log computation can be found in our paper. The ratio of the sliding window's cardinality against the most recent two slices cardinality is equal to the probability that a substream gets a sample H. This probability can be estimated by counting the number of substreams with sample and divided it with k. Therefore, with the computation results of hyperlog-log algorithm plus the ratio of substreams with sample, we can compute the cardinality of the sliding window. At last, with the size of the sample graph, the number of triangles in it, and the estimated sliding window cardinality, we can estimate the triangle count in the snapshot graph with the following formula. As all components in the formula can be continuously monitored, the triangle count in the snapshot graph can also be continuously monitored. The above algorithms are designed for binary counting, but we can easily extend it to weighted counting. In weighted counting, different copies of the same H are viewed as independent. A weighted triangle can also be seen as multiple triangles composed of different parallel edges, as shown in the figure. Therefore, we can replace the hash functions in SWTC with random functions. In this way, each copy of the same H has an independent probability to be sampled, and the estimated H number will also include duplicate edges. Besides, we need to perform weighted counting in the sample graph. Other steps are the same as binary counting. At last, we show the experimental results of SWTC. The dataset we use in experiments are shown in the table. As there are no existing work addressing the same problem, we compare our algorithm with a baseline method, which is a combination of two existing algorithms, partition CT and BPS. Partition CT is an algorithm of binary triangle counting in insertion-only streaming graphs, while BPS is a bounded size sampling algorithm in sliding windows with no duplication. Compared to SWTC, the major drawback of such baseline algorithm is that it has a smaller sample size and thus lower accuracy with the same memory usage. We mainly change two parameters to carry out experiments: window length and sample rate. Window length is the length of the sliding window, with average time span as units. Average time span is the total time span of the dataset, divided by the number of edges. Sample rate is the number of substreams divided by the window length. When the number of substreams are fixed, SWTC and the baseline method has the same memory consumption. We mainly evaluate two metrics in experiments: valid sample size and MAPE. Valid sample size evaluates the number of edges in the sample graph, and MAPE evaluates the average percentage error of the estimated triangle count. We set a checkpoint whenever the sliding window slides 1/10 of the window length, and compute valid sample size and the percentage error at these checkpoints. At last, we report the average value at all these checkpoints as a result. This page shows the performance of the algorithms varying with window length in binary counting semantics. We use two datasets in this experiment: actor and stack overflow. The sample rate is fixed to 4%. From the figures, we can see that with the same memory, SWTC always has a larger sample size and lower MAPE compared with the baseline methods, no matter how the window length changes. This page shows the performance of the algorithms varying with sample rates in binary counting semantics. We use dataset Yahoo network. The window length is fixed to 35 million. From the figures, we can see that SWTC always has a larger small size and lower MAPE. We can also see that with a higher small rate, the sample size grows and MAPE decreases. This is because a higher small rate brings a larger number of substreams, and more small edges will be generated. With the larger small graph, the triangle count estimation also becomes more accurate. This page shows experimental results of weighted counting. We use Stack Overflow datasets, and the window length is set to 4.5 million. Besides the baseline method, we also compare our algorithm with two state-of-the-art approximate triangle counting algorithms for fully dynamic model, WRS and SyncD. These two algorithms only apply to weighted counting semantics. Besides, fully dynamic model requires to get an instruction whenever there is an edge deletion, whether the edge is sampled or not. But in sliding window model, all edges expire automatically. We can only find these expirations in time by storing all these edges in the sliding window and their timestamps. Therefore, for these two algorithms, we need 118 million memory to store the entire sliding window, sample a fraction of edges, and maintain a sample graph. Before this point, they have no MAPE value. They begin to have a commutative accuracy with more than 240 million bytes memory. While SWTC and baseline method can get MAPE below 4% with only 60 million bytes memory. Besides, in weighted counting, SWTC still has a higher accuracy than the baseline method. Besides the above experimental results, experiments about more metrics and parameters can be found in our paper. Thank you for watching. If you want to know more details about our research, please read our paper or listen to our presentation on SIGMOD conference.